2021. Okay. And who is in here for a different course?
Finance.
Finance tutorial. Do you have a copy of your timetable?
Oh, yeah.
Sorry, this is an administration issue.
Yeah.
Is this the first tutorial?
Yes.
Oh, you might. So you're on the timetable. I think you need to.
Thank you.
Okay.
Sorry.
No worries. See, just check on the timetable. It's on my timetable. It's on Signet as well. Sorry. No worries. If you are here for the finance tutorial, I think you might have the wrong room. Your tutor is just finding out now, so I suggest you go and liaise with your tutor outside. Okay. Sorry about the confusion and sorry about the change of room. This room is much better place to teach this course, so I was quite firm with them and suggested that they give us a room which we could actually work with. It will be in this room from now on. Okay, so first thing I'm going to do this lecture is finish off what we started last time, end of lecture 1, then we're going to start lecture 2. So, we got this far in lecture 1 last time. We got up to the definition of conditional probability. Okay, so what is conditional probability? Well, the conditional probability of some event, Si, given some other probable event, Sj, by probable meaning that Sj has non-zero probability, is defined as follows. We say that the probability of Si given Sj is the probability of Si intersection Sj divided by the probability of Sj. And clearly, for that to make sense, one requires that Sj be greater than 0. Okay, something for you to take a look at home. 1, can we say that the probability of Si given Sj is equal to the probability of Sj given Si? And if we can, when can we say that? Okay? Yeah?
Are they not mutually exclusive? Their intersections not empty.
Yes, you should check at home. Yeah. Come and tell me if you can't work it out. Okay? All right. The law of total probability then, which we covered last time, can be expressed in terms of conditional probabilities. So if we let S1, S2 up to Sn be exhaustive, pairwise disjoint and probable, and A is some event of interest, then we can show that the probability of A is the sum of the probabilities of A intersection Sj, so that's the law of total probability, which we covered last week. And now these intersections here, we can just inject the conditional probability formula to replace the intersections. You end up with the sum of the probabilities of A given Sj times the probability of Sj. So when is this useful? This is useful if we know something about subpopulations, but we want to infer something about the population as a whole. Okay, so our Sj's would be subpopulations. That is, for example, okay, let's consider cancer. Suppose we know the cancer risk for people born in Australia and people born overseas. And we know the proportion of people born in Australia and the proportion of people born overseas, then we could say that the probability of cancer is equal to the probability of cancer given born in Australia times the probability of born in Australia plus the probability of cancer given born overseas times the probability of being born overseas. Okay, so what we just require, if we have information on those two subpopulations and we know the proportion in each, then we can construct the total probability of having cancer. So that's why it tends to be useful in general. Okay, very, very important theorem in statistics, which many of you have probably encountered before. It is fundamentally important. Indeed, it forms the basis for an entire branch of statistics called Bayesian statistics. So Bayes' theorem, in a sense, provides answers to questions that are in reverse of total probability. Okay. So let me define what Bayes' theorem is. Let me prove Bayes' theorem as well. And then there's a little example here which you can have a go at in your own time. So Bayes' theorem says the following. If A and B are two probable events, then we have the following. That the probability of A given B is the probability of B given A times the probability of A divided by the probability of B. That is Bayes' theorem. Okay. As I said, Bayes' theorem forms the cornerstone of Bayesian econometrics. The reason for that is it provides a way of updating information from observed events. Okay. You have some prior belief about the distribution of, say, a parameter. Then you have some data. You update your belief about the distribution of some parameter using the data, and you would use Bayes' rule to do that. That's how Bayesian econometrics works. So let us first quickly prove Bayes' theorem. It's very simple. It just uses the definition of conditional probability. So let me just do that quickly. Okay. So Bayes' theorem, we have that the probability of A given B is equal to the probability of A intersected with B divided by the probability of B. Now that is just conditional probability. It's the definition we had earlier. It's the definition of conditional probability. Okay, and we're proving Bayes' theorem, so let me just put a star and Bayes' theorem. Okay, so now what we're going to do is we're going to replace this numerator and we're going again to use the definition of conditional probability. So we have the numerator, probability of A intersected with B is also the probability of B intersected with A, which, using again the definition of conditional probability, is prob B given A times prob A. And again, that is using the definition of conditional probability. So all we've done is use the definition of conditional probability twice, and now all we're going to do is replace this guy here. We're going to plug him in to the numerator over there. So probability of A given B is equal to the probability of B given A times the probability of A divided by the probability of B. And that's it. All we do is use the definition of conditional probability twice. Very straightforward. Everyone good with that? Yes? Cracking. Okay. Let us continue. Back to my desktop. Okay. It's straightforward. So we just considered Bayes' theorem with two events, A and B. It's very straightforward to generalize to more than two events. So we have the following generalization. If S1 up to Sn, mutually exclusive, probable and exhaustive events, and B is some probable event in which we're interested in, And we can say that the prob SI given B is equal to the probability of B. Sorry, is that an I or a J? It's a J, sorry. The probability of Sj given B is the probability of B given Sj times the probability of Sj divided by sum over all possible S's of prob B given S times prob S. So that's a very straightforward generalization of Bayes' theorem. Proof is very similar, so I'm not going to do the proof again. Okay. All good? Yes? Great. Let me talk now about independence of events. This is going to get beyond high school math fairly soon, I promise. I have to go through everything. So, two events, SI and Sj, they're independent if and only if we have the following. That is that the probability of their intersection is the product of their probabilities. That is the definition of independence. That's what we mean when we say two events are independent. We can get, by using the definition of conditional probability, you can get very straightforward that if two events are independent and if Sj is probable, just by injecting this into the numerator in the definition of conditional probability, you get that the probability of Si given Sj is the probability of Si. In other words, whether Sj happens or not is irrelevant for whether Si happens. Okay, it's the probability of Si conditional on Sj is the probability of Si. And again, you just get that by injecting this equation here into the numerator of the definition of conditional probability. All right. Some more things for you to think about at home. If Si and Sj are mutually exclusive, are they independent? Second, can Si be independent of itself? Now, I think the answers to those two are both quite trivial, but I'd like you to have a bash. If you can't do it, or you're confused, let me know. So here we considered independence of two events, Si and Sj. Generalizes very easily to more than two events. Sorry. Which course are you here for? 30?
But actually, I lost the way. So.
Okay, no worries. It's, as long as it's economics.
Oh, yeah.
Yes? Okay, good. That's all right. Grab a seat. Okay. So we can do two events, that's easy. It's also very straightforward to generalize to more than two events. So we say that a collection of events, S1, S2, up to Sj, is mutually independent if and only if, a collection of events is mutually independent if and only if we take any j of them. It is, and for those j, we get that the probability of the intersection of all of them is equal to the product of their probabilities. Okay, so I take any set of events, any group of them, the probability of their intersection should be equal to the product of their probabilities. Okay, so in this case we call the collection of events mutually independent. It's a straightforward generalization of the two-event case. Okay, that is the end of lecture 1. I would say we've covered some very basic concepts in probability. Lecture 2, we are going again to do some more things in probability. In particular, we're going to introduce the notion of a random variable. We're going to start working instead with random variables. Okay. So, lecture 2. We're going to talk about probability and random variables, the relation between the two. We'll start by defining random variables. We'll consider univariate random variables, in which case we'll talk about discrete random variables, continuous random variables, we'll talk about distribution functions, and we'll talk about probability density functions. After we've done the univariate case, we'll move on to the bivariate and then multivariate cases, in which case we'll look at the joint distribution, joint density, and probability functions. We'll also look at how to obtain a marginal distribution. We'll look at a notion of independence of random variables. And then we'll look at conditional distributions as well. So again, and throughout I'm going to do some examples to make sure that everyone's following. All right. So random variable. Why are we interested in random variables? We've just spent 2 hours talking about events and probabilities. Who cares about random variables? So in real life, it's often rather difficult to identify the sample space, the experiment, the events, in a formal fashion like we've done so far. And often we're interested just in the probability of events that are described very simply. Okay, so what is the probability of getting a total of 10 when 2 dice are rolled, for example? Now, it's easy to attach numbers to the sum of 2 dice throws, right? It's a very easy thing to do. So for a given experiment and resulting sample space S, suppose that we can assign a real number to each simple event. Okay, I take an event, a simple event, I give it a number, right? Such a real number is referred to as a random variable. That's all a random variable is. A random variable is a real number which corresponds to a simple event. So, before we conduct the experiment, for example, rolling 2 dice twice, we don't know what this real number is going to be, but we can enumerate all possible values that this real number can take. We can attach probabilities to them, and then if we combine the above two, we have a random variable. So formally, and I should say, if you roll 2 dice twice, a sensible random variable to measure the probability of getting a 10 when 2 dice are rolled, a total of 10, would just be to assign a random variable, which was the sum of the 2 results. So if you got 1, 1, you would have 2. If you got 2, 2, you would have 4. If you got 5, 5, you would have 10. That's your random variable. Okay, formally, a random variable is a real valued function defined over the sample space. So each simple event is associated with a number. Okay. So broadly speaking, there are 2 types of random variables. There are discrete random variables and there are continuous random variables. A random variable is said to be discrete if it can take a countable number of values. So for example, if X is the number of television sets sold in a Harvey Norman store in a given year, that would be a discrete random variable because you can't sell half a television. Well, you could, but I wouldn't. Or X could be the number of votes received by a candidate in an election. Okay, it's a discrete random variable because it takes integer values. Conversely, we say that the random variable is continuous if it can assume all real values in some interval or intervals. So, for example, heights of adult males would be continuous. Okay. Or the daily maximum temperature during the month of January, that would also be continuous. It can take any value. Okay. So, wrong class?
Sorry. The room is changed.
Yes, I thought it might be. Okay. He was polite for 5 minutes. I knew when he sat down that he was in the wrong place. Anyway. Okay. Notation. We use uppercase letters, conventionally, to refer to random variables themselves. We use lowercase letters to refer to fixed values that a random variable can take. Okay? So big X will represent the random variable. Small x will represent a particular value that big X can take. And then, if we add a little subscript to the small x's, that would usually be used to denote data. Okay, so xi would be the ith realization of the random variable x. And if we have, if I runs from 1 to n, that means we have a sample of size n. Okay, so xi will usually refer to data. which on this course will be collected under random sampling. We won't talk about non-random sampling. We define random sampling in Lecture 1. It means that our observations are independent and identically distributed. Okay. Probability density distribution functions of random variables. Right, so we've got a random variable. How do we describe the values that that random variable can take and how likely they are? We should often know the range of the random variable. So is it discrete? Is it finite? Is it countable infinite? Or do we have a set of intervals in which it can lie? We should know which values that random variable can take. And associated with each value the random variable could take, we should have some information on the probability that it does so. So we will look at three things. Firstly is what's called the distribution function. You might also hear it referred to as the cumulative distribution function. We use the distribution function for both discrete and continuous random variables. Second thing we'll consider is something called a probability function. A probability function is only used for discrete random variables. So it's the discrete counterpart of a probability density function. Finally, a density function, or you might hear it called a probability density function. These are just used for continuous random variables. Okay, so let us start with the distribution function. So the distribution function, or sometimes, as I said, the cumulative distribution function, is defined as follows. The distribution function of a random variable, y, capital Y, at a point, small y, we denote that by capital F underscore capital Y of y. Okay, that's how one denotes a distribution function. That is the probability that the random variable, capital Y, takes a value smaller than the point lowercase y. That's the definition of a cumulative distribution function, or distribution function. I'm sure you've all seen that before. I hope you've all seen that before. So what I'm going to do next, I'm going to prove some properties of distribution functions. In order to do that, I need an important result, which is called continuity of probability. Okay, so in a minute, I'm going to prove some properties of distribution functions. The proofs are going to rely on an important notion of probability, which is called continuity of probability. So I'm just going to segue to talk about continuity of probability for a moment, and then we'll get back to distribution functions. Okay. So continuity of probability is a very important result. It looks at what happens in the limit for sequences of events. So first we begin with the definition. If Aj denotes a sequence of events, an infinite sequence of events, then we say that this sequence of events increases to A being another event, if A1 is a subset of A2, is a subset of A3, so on and so forth, and the union of all of my A's, of all of my AJ's, is equal to A. In that case, we say that the sequence of events, Aj, increases to A. And we say it decreases to A if we just swap the direction of these guys here. So we say it decreases to A if A1 is a superset of A2, is a superset of A3, and so on, and the union of them all is A. Okay, so there's a definition. We have a sequence. That sequence can either increase or decrease to some event A. We'll use this in a minute, so you'll see how it works when we apply it. And then we can say two things. The first thing we can say is, given that such a sequence, suppose we have a sequence of events increasing to A. Then we have the following. We have that the limit, as j goes to infinity, of the probability of Aj is equal to the probability of A. Okay? That's called continuity of probability. We can get the same result the second theorem, I'm going to prove the first theorem in a moment, we can get the same result if the sequence of events decreases to A. That is, that if a sequence of events decreases to A, the limit j going to infinity of the probability of Aj is equal to the probability of A. Okay, so let me just prove this theorem quickly. It's not particularly complicated proof, but let me do it nonetheless. I think it's important you know where these things come from. Alright, so I'm just going to prove the first theorem, this one. The proof of the second theorem is almost identical. Okay, so you can have a stab at that yourselves if you're interested. I'm just going to prove the first one. Okay, let me go to my document cam. So, all right. So let's have a new page. Let us prove the continuity of probability. Sorry, just bring this over here to make sure it gets captured. Right. Continuity of probability. Okay. So we're going to consider the first theorem, which is that we have events increasing to A. Okay. So if the events are increasing to A, then it must be that Aj is a subset of Aj plus 1. That's the definition, it's the first part of the definition of events increasing to A. Therefore, we have the following. We have that Aj intersected with Aj plus 1 is Aj. Okay, because Aj plus 1 contains Aj. All right, now let us define a different event. Let us consider Bj plus 1, which is going to be Aj plus 1 intersected with Aj complement. Okay. Moreover, for notational convenience, let us do the following. Let us define, let's define an event A0, and let's call that the empty set. So that B1 is equal to A1. Okay. So, it's quite straightforward to see. You can verify this, that the sets B1, B2, and so on are disjoint. And we also have that the union j equals 1 to n of bj is equal to a n. Moreover, we have that the union j equals 1 to infinity of bj is equal to the union j equals 1 to infinity of aj, which is a. because our events AJ are increasing to A. Okay, you can verify those two things. We're going to use those two properties. All right, so now we're ready to go. So let us take the probability of A. Well, using this here, this is the probability of the infinite union of Bj. So that's just using that there. Okay, the Bj's are disjoint, so that is the sum from j is equal to 1 to infinity of the probabilities of each Bj. That was the third axiom of probability that we introduced in the last lecture. Okay, now a little trick. The trick is as follows. We can always write an infinite sum as the limit of n going to infinity of the sum from I is equal to 1 to n of the probability Bj. So instead of writing the sum j1 to infinity, I just write the sum, j, that should be, j1 to n, and then I take the limit of n to infinity. Same thing. Okay. All right. So now we have this. Keep the limit. Keep the n to infinity. And what we have is that this is the probability of the union j equal 1 to n of Bj. And from this line to this line, again, we're using that the Bj's are disjoint. We're going backwards this time. So we're saying that the sum of the probabilities is the probability of the union, because they're disjoint. Okay. Last thing. Now we're just going to use this, that the union j is 1 to n of Bj is an. So I'm just going to inject that in there. So we still have the limit of n going to infinity of the probability of an. So that is just using this here. Just plugging that into there. All right, and that's it. We have that the probability of A is equal to the limit as n goes to infinity of the probability of an if the events in the sequence aj increase to A. Okay, so that's continuity of probability. Everyone okay with that? What I would recommend, if you find these proofs hard to follow, first, don't need to scribble down everything. I'm going to upload everything I write, and there's going to be a lecture video as well. So I would recommend you pay attention to what I'm doing rather than frantically trying to write everything I write. If you do have issue with proof, take a look at the lecture recording and take a look at what I've done, go through every step yourself. Okay? I know there was an issue with the lecture recording for 7321 last week. I don't know if you've seen, but I sent you an email this morning, and I've posted the lecture recording online. IT services are dealing with the problem. It'll be resolved soon enough, and they'll just appear in the normal way. But for this week, for week 1, you'll find the lecture recording as a file in week 1 learning resources, if you can't find it in the normal way. Okay? Okay. Good. Right. Let me go back to my desktop. So, we've just proven something called the continuity of probability. Now what we're going to do is we're going to use this result to prove some things about distribution functions. So some properties of distribution functions. We have the following. Firstly, f(y) of y, the distribution function, is defined for all values of y in the range minus infinity plus infinity. Now, it might well be 0 or 1 over a large proportion of that range. Nevertheless, it's still defined. The lower limit of the distribution function is 0. That is, as y goes to minus infinity, f(y) of y goes to 0. The upper limit of the distribution function is 1. That is, as y goes to infinity, f(y) of y goes to 1. Now, remember, the distribution function is a probability, so it can never go outside 0, 1. And it's fairly obvious from the definition of the distribution function. I mean, I'll prove it in just a moment. Where were we? Fairly obvious from the definition of the distribution function that as small y goes to minus infinity, the probability that large y is less than small y is going to go to 0. Something can't really be smaller than minus infinity. And similarly, as small y goes to plus infinity, the probability that the random variable big Y is going to be less than that is going to go to 1. Okay. Fyy is non-decreasing. It's a non-decreasing function. As small y increases, Fy of y does not go down. It can stay the same, but it will not go down. And it is continuous from the right, meaning that this limit here exists. So Fy of y is equal to the limit of Fy of y plus delta y, and as delta y goes to 0, one will obtain this relationship. That means it's continuous from the right. Okay, it is not continuous from the left. Okay, it's continuous from the right. So let's prove some of these properties. What do I want to start with? Let's start with the easiest one, which is that it is non-decreasing. Okay, that's the most straightforward one to prove, that it's non-decreasing. So let me hit my dot cam. Let's have a new page. Now, what I'm going to prove is that fx of x is non-decreasing. By the way, I'm changing to x instead of y deliberately, because you wouldn't believe the number of times that if I prove everything with y, and then ask the students to do the same, but calling the random variable x instead, they can't do it. So I'm swapping here. I had y in the notes, now my random variable is called x. Alright. So, this is really easy. All we're going to do is we're going to construct two events. We're going to show that one event is a subset of another. And last week we proved that if one event is a subset of another, then it has smaller probability. That was something we proved last time. So, consider x1 less than or equal to x2. Right, just take two numbers, x1 and x2. Okay, so the event that our random variable big X is less than or equal to x1 is a subset of the event that our random variable big X is less than or equal to x2. So these are events, and I've written the events in terms of the random variable x. This one is a subset of the other. Why? Because if x is less than x2, then clearly x is less than x1. Why? Because x2 is bigger than x1. Sorry, other way around. Okay. All right, anyway, they're a subset. Next. So last time we showed that the probability that x is less than or equal to x1 must then be less than or equal to the probability that x is less than or equal to x2. We showed that last time. That was one of the results we derived last week. Well, what is this? This is just CDF evaluated at x1. What is that? It's just the CDF evaluated at x2. And that's it. We're done. If x1 is smaller than x2, then fx of x1 is smaller than fx of x2. And we just used one result which we proved last week. Okay. So hopefully that's quite straightforward. Let us now show that the lower limit is 0. So that the lower limit of fx of x is 0. Okay, so here we're going to use continuity of probability. That's why I derived it earlier. So what we're going to do is as follows. We are going to consider a sequence of events. I'm going to call them AN. And AN is going to be equal to the event that the random variable x is less than or equal to minus n. Okay, that's an event AN. Right. So, let's AN going n is 1 to infinity. That sequence of events, if I define them that way, is decreasing to the empty set. So as n is getting large, AN is going to the empty set. Why? Because as n is getting large, minus n is going to minus infinity, and the set where x is less than minus infinity is empty. Okay. So now, let us use the continuity of probability which we derived earlier. That is, that the lim, as n goes to infinity, of the probability of AN is, well, let's write a little bit, that is the lim, n goes to infinity of the prob x less than or equal to minus n. You can see then that that is the lim n going to, what did I do? Okay, sorry. So this guy is equal to the probability of the empty set, because our sequence is decreasing to the empty set. So that's using, going from there to there, is using continuity of probability. And we have that that is 0. And that's it. Why? Because this is fx of minus n. This guy is fx of minus n. So that's the end. If n goes to infinity, minus n goes to minus infinity. And we use continuity of probability to go from this line to that line. And the fact that our sequence of events is decreasing to the empty set. So that is the end. Everyone happy? Yes? Okay, good. So that's non-decreasing. Sorry, that is that the lower limit is 0. Let me now do right continuity as well. Okay. So I'm going to now prove that fx of x is right continuous. Fx of x is right continuous. Okay. So we're going to follow a very similar approach. So what we're going to do is as follows. Let us consider a sequence of real numbers such that the first one is bigger than the second one, is bigger than the third one, and so on. And let us suppose that those numbers are going to x. So you might have seen the notation. What this means is that we have xn decreasing to x. You might have seen that notation before. If you draw a downwards arrow, it means that your sequence xn is going from above to x. Why are we going from above? Because we're trying to prove right continuity. If we were going from below, we'd be trying to prove left continuity. No? Yes? Okay, good. Then you'll learn something today. Okay. So, right. Let's use this sequence of real numbers now to define an event. So we let an be the event that x is smaller than xn. Okay, that's the event we're going to be interested in. And now what we're going to do is we're going to apply continuity of probability to the sequence of events an. So, what can we say about this sequence of events an? Sequence of events an, running from 1 to infinity. Well, it's decreasing to an event a, which is big X less than or equal to little x. Sorry, that's gone off the edge. There we are. That sequence of events is decreasing to a big X less than little x. Why? Because xn is going down to x. Okay. So now we're ready to apply continuity of probability. So let us do that. So let's apply the definition of continuity of probability. That is the lim as n goes to infinity of the probability of an is equal to the probability of a. Or in other words, the lim as xn decreases to x of the probability that x is smaller than xn is equal to the probability that big X is less than or equal to small x. That's just injecting the definition of an and a. Okay, so then we have that the lim as xn decreases to x of fx of xn is equal to fx of x. That means that this function is right continuous. If you imagine it on paper, as you come in from the right, you're coming in from a large value of x and you're decreasing x. Yeah? As x decreases, we're going from right to left. Okay, if you were to have a graph on paper. That means that's what this little symbol here denotes. And so we have right continuity if the limit, as we come in from the right, as we decrease x, is equal to fx of x. And we have x there as well. That's the definition of right continuous. Okay. Okay. Square. If we were to try and do the same for left continuous, what would change is you would want to consider an increasing sequence of events. You would here have xn going up to x, and it wouldn't work. Have a go. See if you can find out why it doesn't work. It doesn't work, in general. So it's not left continuous, but it is right continuous. Okay. Any questions? Is everyone bored to tears? Possibly. I think it's a good time to take a break. So let's start again at 1 o'clock. Okay, 8 minutes. Okay, let's go again. So, before we had the break, we proved that the lower limit is 0. The proof that the upper limit is 1 is very, very similar. So I leave that as an exercise for those of you who are interested, which all of you should be. We proved that it's non-decreasing. That was the easy one. And the last one we did, which was a bit harder, is that it's continuous from the right. Okay. So that's pretty much everything you need to know about distribution functions. Distribution functions, as I said, apply equally to continuous or discrete random variables. So now what we're going to do is we're going to look at probability functions for discrete random variables, and then what we're going to do is look at probability density functions for continuous random variables. Okay, so let us now focus on the case where we have a discrete random variable y. We'll let y1 up to yk represent the values that this random variable can take. It can take k values. The probability function, all it does is it assigns a probability to each of those values. Okay? We write, you might see it written, so we'll call the function lowercase p. Pyi is very simply the probability that the random variable takes the value yi. That's it. It's between 0 and 1 at all values which y can take, and it's 0 everywhere else. Okay, the probability of y taking a value outside its range is 0. But at every other point, it just gives the probability associated with that point. Okay. So what is Py? It's the sum of all probabilities attached to all the sample points in the sample space that corresponds to the random variable taking on value small y. The relationship between the probability function and the CDF is as follows. The CDF is just equal to the sum of the probabilities of all values of yi less than or equal to y. So in other words, f of y, should be fy of y, my apologies, is just the sum of the probabilities over all values of yi which are smaller than y. Right? That's pretty obvious, I think. Okay. The graph of the density function, so the graph of the density function, or the probability function, is a graph with spikes. So at each discrete value, you'll see a spike which will give the probability associated with that value. And the distribution function is going to be a step function. Okay, that's what it'll look like for a discrete random variable. Distribution function will be a step function. Okay. So, that was discrete. Now, continuous. Unless there was something I wanted to prove or check. No, there wasn't. Good. Continuous random variable. So now if y is a continuous random variable, let's suppose it takes values in the interval a, b. The density function of y, this time we use an f instead of a p. Small case fy of y is a non-negative function such that the function is 0 for all values outside the range ab. Why? Because our random variable takes values in the interval ab. And inside the interval ab, not inside the interval ab, just in general, the probability of large y being smaller than small y, that's the definition of the CDF. That is the integral of the PDF between minus infinity and the value of y. And in this case, because we were saying that y takes values between a and b, you can forget about the minus infinity part, you can just start from a. Because it's 0. If it's less than a, then fyy is 0. Okay. I take it many of you have probably seen that before. If the distribution function fy of y is differentiable, then we obtain the density function by differentiating it. That is, the density is the first derivative of the distribution function. The PDF is the first derivative of the CDF, provided that the CDF is differentiable. So, a few things worth mentioning here. The CDF and PDF are equivalent characterizations of a probability distribution or random variable. If you have the PDF, you know everything. If you have the CDF, you know everything. You don't gain anything by knowing one when you already know the other. Number 2, the CDF always exists, and it's well defined for any random variable. The PDF exists just for continuous random variables, and it actually may not exist for all continuous random variables. It doesn't exist for all continuous random variables. One requires differentiability of the CDF for the PDF to exist. Having said that, on this course, we're only going to consider cases in which the PDF does exist. We're only going to consider continuous random variables and their associated distributions for which we can work with a PDF. But just note that it doesn't always exist. Okay, what do PDFs and CDFs look like then? Well, on the top panel here, we have the CDF of some random variable x. So the way you read this, on the x-axis, you have all the values that your random variable x can take. On the y values, you have the probability that the random variable x is less than or equal to the value on the x-axis. So as we showed earlier, the lower limit is 1. It's non-decreasing. Sorry, the lower limit is 0. It's non-decreasing. Upper limit is 1. So that's what your CDF will look like. Now, if you differentiate your CDF, you get a PDF. And the PDF will look, for this random variable, it will look like this. So at each point in the PDF, it's telling you the relative mass of probability compared to all the other points. And so here, for the CDF at this point here, we look at the point minus 15, so that's the probability that x is less than or equal to 15. We take the same point on the CDF, on the PDF down here, and we integrate between minus infinity, and here we would get 0.2. That corresponds exactly to the 0.2 which we get here in the CDF. Okay. So you get the value of the CDF by integrating the PDF up to that point. Is that clear? Yep. Okay. And that's what they would look like in a typical example. All right. So that's univariate random variables. For the remainder of this lecture, we're going to talk about multivariate random variables, but we're going to focus mainly on the bivariate case because everything for the bivariate case is relatively simple. Things get much more complicated when you consider the multivariate case, but the intuition is basically the same. Just the formulas get longer. Okay, so let us now consider jointly distributed random variables. So up to this point we had a sample space with one random variable. Now we're going to have more than one. We're going to have two for most of the rest of the lecture. Sometimes I'll tell you what the generalization is when we go to n. So the cumulative distribution function and probability density functions of each of those random variables, when we have more than one, we'll put the word marginal in front. So when you see marginal, that means just one of our random variables. So marginal PDF is the of x is the PDF of x, ignoring any other random variable. Okay, I'll show you how to get those in just a moment. You can also have a marginal CDF or a marginal distribution function. In general, you won't usually see the range for the random variables being specified. Where it isn't specified, just consider minus infinity to plus infinity. So when you're working with integrals or whatever, if you don't know the range a random variable takes, just put in minus infinity plus infinity. In the case of discrete random variables, the range is given by the range of each of the random variables. That is, if x can take on values 1 and 2, y can take on values 3 and 4, you've just got to consider all possible pairs. That will give you the range of x and y. The distribution of density functions for bivariate or multivariate random variables, they'll be associated with the joint distribution of the random variables, and we'll show that we'll work out what that association is now in the rest of this lecture. All right, let's begin with the discrete case because it's easier. And we're just going to do bivariate. So if we have discrete bivariate random variables, x and y, well, the range of those bivariate random variables is just the product of the ranges of the two random variables. So if x can take values x1 up to xn, y can take values y1 up to yn, say, then we just need to consider all possible combinations of x and y. That would be the range. The probability on the on the bivariate random variable x and y is given by the probability function for all possible pairs of values of x and y. That is, if we want to characterize the distribution of x and y entirely, all we have to do is attach a probability to each pair of values that it can take. If we do that, we know everything. Okay, so the probability function just attaches a probability to all possible values that x, y can take. So let us just to make sure everyone's on the same page, let's just do a quick example. Suppose we've got a bivariate case, x and y, and they can each take on two values. Okay, so then what we would need to do, if they can each take on two values, then there are four things that can happen, right? We can have x equal to x1, y equal to y1. We can have x equal to x1, y equal to y2. We can have x equal to x2, y equal to y1. And we can have x equal to x2, y equal to y2. We attach a probability to each of them. In this example, the probability of getting x1, y1 is 0.4. Probability of getting x1, y2 is 0.3. Probability of getting x2, y1 is 0.2. Probability of getting x2, y2 is 0.1. And now you know everything there is to know about probability, about the distribution of x and y. That's all the information. So from this information, this is the joint distribution of the two. We can compute different things. We can compute the marginal probabilities, and we can compute the conditional probabilities. So I'll show you quickly how to do that, because it's very straightforward in the discrete case. So let's do that for this example. So I'm going to show you how to compute some marginal and some conditional probabilities from this information here. Okay. .cam. So let's go here. So this is our discrete bivariate example. So, let us compute the marginal probability that x is equal to x1. Probability that big X is equal to x1. Right. To compute the marginal probability, all you need to do is sum over all possible ways in which x can be equal to x1. Right? Well, one way that x can be equal to x1 is if y is y1. Right, that's one way, that's one case in which x can be equal to x1. Another case is if x is equal to x1 still, but y could also be equal to y2. Y can't take any other values, x is x1, so those are all the possible probabilities associated with all the ways in which x can be x1. You sum them up. Okay, summing in the discrete case is the equivalent of integrating in the continuous case. Right? We sum those two up. So, what was the first one? It was 0.4. What was the second one? It was 0.3. Overall, 0.7. Okay, so to get the marginal distribution of x, just sum the probabilities over x equal to x1. I could do the same for x is x2. I could do the same for y equals y1. I could do it 4 times. I think it's pretty trivial, so I'm not going to. Okay, that's how you compute marginal probabilities in the discrete case. Let's do one more. Why not? Let's do. This is easy, right? So let's spend more time on this rather than the hard stuff. X equals x2. That can happen in 2 ways. You can have x equal x2 and y equal y1, or you can have x equal x2 and y equal y2, sum them both up. First one was 0.2, second one was 0.1, so you get 0.3. Right, that's how to obtain the marginal distribution. Okay, that's easy. Conditional distribution. So let us now work out the probability, for example, that x is equal to x1 given y is equal to y1. Okay, we just use the following formula. That is the probability that x equals x1, y equals y1, divided by the probability that y equals y1. Right, that's how you compute conditional distribution. So we didn't work out the probability that y was equal to y1, which is on the denominator. So how do we do that? We do exactly what we did with the x's. We just sum over all ways in which y can be equal to y1. So it is prob, well, x could be x1, and x could be x2. So we fix y at y1, sum the probabilities over all values that x can take. That should be, from our example, 0.4 plus 0.2, which is 0.6. So that's the denominator. Then, so we've got something over 0.6. In the numerator, we've got prob x x1, y is y1, which from our example is 0.4. So it's 0.4 over 0.6, which is 2/3. Everyone good with that? Yeah? Quite easy, simple arithmetic. Okay, good. Right, let us continue. So that's that's everything you need to know about discrete random variables. You've got the joint distribution, you can compute the marginals just by summing probabilities, you can compute the conditionals just by using the formula. Okay, let's go back to the desktop. Right, so we know how to do everything in the discrete case. Why have you stopped working? Okay, good. Let's now consider the continuous case, because it's a bit more interesting, and it'll be what you encounter most of the time in econometrics. So the range of each of the random variables should be specified. It could be minus infinity to plus infinity. It could be 0, 1, whatever. The joint CDF of x and y, we define it as f xy of x comma y. That is just the probability that big X is less than little x and big Y is less than little y. That's what we call a joint CDF. Okay. We've got two random variables, so it's got two arguments, small x and small y. If the joint CDF is differentiable, then the joint density function is just obtained by differentiating with respect to x and y. So it's d2 fx of x and y by dx dy. Just differentiate with respect to x and y sequentially. The distribution function and the density function, they're related as follows. So the CDF gives us the probability that big X is less than little x, big Y less than little y. And that is the same as if I integrate between minus infinity and little y, minus infinity and little x of the joint PDF. Right, I've just got a sum. Now, before I had one random variable, now I've got two random variables. Instead of integrating once, I integrate twice. Moreover, it should be the case that if I integrate the joint PDF over both dimensions, over both arguments, between minus infinity and plus infinity, I should get 1. Otherwise, it's not a PDF. It has to integrate to 1 when I integrate in both dimensions. Okay. How to obtain marginal distributions then? So we've got a joint distribution. We would like to obtain marginal distributions. So in the bivariate case, with PDF fx of x and y, we could be interested in the marginal distribution of x, just x, and its properties. So how do we get the marginal distribution of x if we've got the joint distribution of x and y? Well, what we do is the following. I'll prove it to you in just a moment. If f x and y of x and y is the joint density, we would like to get the marginal fx of x. We obtain it by integrating the joint density with respect to y between minus infinity and plus infinity. In the discrete case, we summed over the values of y to get the marginal. In the continuous case, we integrate over the values of y. Yeah? So the marginal is equal to the integral of the joint over y. So you integrate out the other variable. When you hear someone saying integrate out, all they mean is integrate with respect to the variable in which you're not interested in. Okay. Let me prove that, because I think it's useful for you to be able to do it. How are we time-wise? Okay, good. So let's prove that we integrate the joints to get the marginal. Okay. So this proof is going to use something called the second fundamental theorem of calculus. So let me just write down what is the second fundamental theorem of calculus. second fundamental theorem of calculus. Okay, so we have for some function g, which is continuous on an interval, say ab, we have the following result. So if you've got a continuous function defined on some interval, what we have is this. We have that d by dx, so if we take the partial derivative with respect to x of the integral between a and x dt dt. So if I integrate my function between the interval of a and x and I differentiate, what do I get? I get g of x. That is the second fundamental theorem of calculus. Okay, if I differentiate an integral, upper limit of the integral is x. If g is continuous, I get g of x. Okay, so now we're going to use that. So, what I'm going to do now, I'm going to show you how to get the marginal distribution of continuous random variables. Okay. So, let us do the following. What do I want to do? All right. Let's consider the following. So let's consider the integral between some lower limit, which I call x0, and x, of the marginal distribution of x like that. Okay, so I'm going to integrate f of x between x0 and x. Okay. So what is that? Well, we can express that in probabilities. It is simply the probability that big X lies somewhere between x0 and little x. Okay. So what is that? Well, that is the probability that x lies between x0 and little x, and y lies between minus infinity and infinity. Y has to be something, and it has to be something between minus infinity and infinity. Okay. So, how do we get that? Well, I just need to integrate my joint PDF. Over x I need to go from x0 to x, and over y I need to go from minus infinity to infinity. That's what will give me this probability here. Right? So, let's do x first. We go x0 to x. And now let's do y. Well, we go from minus infinity to infinity. Here we have the f x y. I'm going to integrate x with respect to t, so I'm going to put a t there. I'm going to put a y there. Here we're going to have a dy. Here we're going to have a dt. Right. So all I'm doing is if this were discrete, I'm just summing up all the values of x between x0 and small x, and all the values of y. It's not discrete, so I'm integrating instead. Yep, that's what gives me that probability. And now, just to make life a bit simpler, I'm just going to put a bracket here. Because we're going to do something with that term in brackets in just a moment. Okay, so here, now what we're after is fx. What I did was I actually integrated fx. So now what I'm going to do is I'm going to use the second fundamental theorem of calculus to get fx of x. Right, so we're going to have that d by dx of the integral between x0 and x of fx t dt. Well, what is that? By the second fundamental theorem of calculus, that is fx of x. So I'm after fx of x. What do I need to do? I need to differentiate this guy with respect to x. Yep. All right, let's do it. So, d by dx. What am I after? I'm after the integral between x0 and x. Then I'm going to keep my bracket there. Integral between minus infinity and infinity, f x y t and y dy. Then I'm going to put a dt there. All right. Now what I'm going to do is apply the second fundamental theorem of calculus again. And what is this? Well, all I need to do when I differentiate with respect to x, I can get rid of this outer integral, and then I'm just going to replace t with x. That's it. So, again, by the second fundamental theorem of calculus, it is the integral between minus infinity and infinity of f, x and y, dy. So here we used, I'm going to call it SFTC, second fundamental theorem of calculus, we used there. And again, we used it here. So our g function was everything in brackets when we applied the second fundamental theorem of calculus the second time. Okay. So we took g to be everything in this bracket. So we just used the second fundamental theorem of calculus twice. Okay. We have that this was equal to fx of x. We also have that the same thing was equal to the integral with respect to y. So this is just fx of x. And that is the end. So I'll just go through that again briefly to give you the steps. So we start out with this guy. Why do we start out with this guy? Because we're going to apply the second fundamental theorem of calculus to it. This guy we can write as the probability that x is between x0 and small x. Now, we don't change anything when we say that x is between x0 and small x, and y is between minus infinity and plus infinity. Y has to be between minus infinity and plus infinity. Right? So we don't change anything when we add that. Now what we do to get this probability, we integrate, and so we integrate over the possible values of x and the possible values of y. Well, x goes from x0 to x, y goes from minus infinity to infinity. We integrate the joint PDF with respect to y, and I've used t here because I used x in an earlier notation. Okay? You just do a double integration over the bounds you're interested in. Now, so we've worked out what this guy is. If we differentiate this guy, by the second fundamental theorem of calculus, we get this relationship. Right? If I differentiate the integral of fx of t between x0 and x, I get fx of x. Okay. This guy here, on the left-hand side, what is it? This integral here, well, we worked that out a second ago. It's this guy here. Right? So we just plug that in there. We're differentiating. Now we apply the second fundamental theorem of calculus again. This time, our g from the second fundamental theorem of calculus, remember this was the second fundamental theorem of calculus, we need to define a g. This time, our g function is everything in brackets here. So, all that one does is replace the t with an x, and you're done. And that's equal to fx of x. Okay? So we just applied second fundamental theorem of calculus twice. All right. Good. How are we doing for time? 15. Any questions? Everyone happy? As I say, I don't expect you to get these proofs first time. I'll take your questions. I don't expect you to get these proofs first time. What I do expect you to do, if you don't get it, go through it again. There's going to be a lecture recording. You're going to do things in tutorials as well. Okay? So if you're sitting here thinking, oh my God, I don't understand, that's fine. Okay? You might not understand first time round. Okay, question? Okay, great. Okay, good. Let us go back to the desktop. How are we doing? 15 minutes, all right. How are we? Okay. So, we've now proven what we probably all know is that to get the marginal from the joint, we integrate with respect to the other variable. Okay. How then do we talk about independence in the bivariate case? So, definition. I say that two random variables, x and y, are independently distributed if and only if their joint distribution function and their density, if it exists, is equal to the product of the marginal distribution functions. That is, that fxy of x and y, so I should really make these bigger, shouldn't I? I'll expand them. I don't know why they look so small. Fxy of x and y is equal to the product of fx of x and fy of y. That's independence. Okay? Or equivalently, if the PDF exists, it's that the joint is equal to the product of the marginals. And importantly, the fact that the joint is equal to the product of the marginals should hold over all possible values of x and y. It's not enough for it to hold at one value. It's got to hold everywhere. So that's independence. You either have that the product of the joint CDF is the product of the CDFs, or the joint PDF is the product of the PDFs. So suppose we have independence, and suppose that our random variables x and y have exactly the same distribution. Then we would call them independently and identically distributed. You might hear the term IID. IID means that two or more random variables are independent and have the same distribution. Okay? Say that again. IID stands for independently and identically distributed. That means that the random variables are independent and they have the same distribution. That is, fx of x is equal to fx of y. Okay. How do we talk about conditional density function? Well, let's consider the density function of x conditional on a given event. Suppose that x and y lies in some plane S. Okay, if x and y lie in a plane S, and let's suppose that the probability that x and y lie in that plane is greater than 0. Then the conditional density is given as follows. We say that f x and y of x and y conditional on the plane S is equal to, well, it is just the joint PDF divided by the probability of lying in that plane. Okay. It's a plane, by the way, because we have two dimensions. We have an x and a y. Okay. Clearly a special case is when that plane is a point. A special case is the conditional density function evaluated when x is a particular point, small x. So that is fxy of y given x is, f of y given x of y given x is just the joint divided by the marginal. So it's f of x and y divided by f of x, provided that f of x is non-zero. Yep. It's a bit small, isn't it? Sorry, I'll make it bigger. Okay. Did I want to prove that? I think probably not. So I think we'll just finish with a couple of examples. Okay. So some relatively straightforward examples. We're just going to, given a bivariate distribution, we're going to derive a marginal distribution of x and y. We're going to ask, are they independent? We're going to compute some probabilities as well, but I won't finish, so I'll just get as far as I can in the next 10 minutes. Okay. All right. So let us go to my .cam. So I'm going to do example 1, maybe not all parts. We'll see how far we get. So in this example, we have a joint distribution uniform on the unit square. Okay, fx and y lie between 0 and 1, and the density is 1 everywhere on that square, and it's 0 everywhere else. Okay, and we're going to compute the marginals. We're going to ask, are they independent? We're going to compute the probability that x is larger than y. We're going to compute the probability that x squared plus y squared is less than 1. And we're going to compute the distribution conditional on x being smaller than y. All right, so let me go to my .cam. So part 1, we're going to derive the marginals. That might be as far as we get. We'll see. Okay. So let's derive the marginal of x. So we have fx of x. To get the marginal, we need to integrate out y. The general formula is this. We integrate between minus infinity and plus infinity the joint distribution with respect to y. Okay. So we're looking from minus infinity to plus infinity, but we know that y actually only has positive probability in between 0 and 1. Right? So this is the same as 0, 1, fxy of x and y. Because y only has, that we only have probability mass for y between 0 and 1. 0 everywhere else. Okay, so now we can plug in what this guy is. On the range 0, 1, this guy is 1. So it's the integral between 0 and 1 of 1 dy. That's directly from the question. And that is if x is between 0 and 1. We need x to be between 0 and 1 as well for this guy to be 1. So what is that? That is the integral between 0 and 1 of 1 is 1. So it's 1 for 0 less than x less than 1. What if x isn't in that bound? If x is not between 0 and 1, then this is 0. So it's the integral between 0 and 1 of 0 dy. Otherwise, which is 0. So in sum, fx of x is 1 for 0 less than or equal to x less than or equal to 1, and it is 0 otherwise. Right, so what do we do? We need to integrate y between minus infinity and plus infinity. In practice, we can forget about the minus infinity plus infinity and replace it with 0, 1, because y only has positive probability if it's between 0 and 1. So we would integrate between 0 and 1. Now, if x is between 0 and 1, if x is between 0 and 1, then f of x of y is 1. So that's the case we do first. We integrate 1 between 0 and 1, you get 1. I trust you can all do really basic integration. If you can't integrate 1 between 0 and 1, let me know urgently in office hours, and we'll discuss it. So that's if x is between 0 and 1. Second case, if x is not between 0 and 1, then the PDF was 0 from the question. We integrate 0 between 0 and 1, we get 0. To sum up, we have that fx of x is 1 for x between 0 and 1, and it's 0 otherwise. Okay, everyone happy with that? Yes? Good. Right, that's part 1. How are we doing for time? Okay, not long. Let's do part 2. So part 2 asks us, are x and y independent? Okay, so to know whether x and y are independent, what we want to do is we want to check whether the joint PDF is equal to the product of the marginal PDFs. We've got the marginal PDF of x, we need to get the marginal PDF of y, but because of the symmetry in the question, you can just see immediately in the previous part, if we replace if we replace x with y in part 1, everything is exactly the same. It's all symmetric. So we have that the marginal distribution of y is this. It's 1 if y is between 0 and 1, and it's 0 otherwise. That's because of the symmetry in the question. Otherwise, you'd have to work it out again. I'm going to skip that because it would just be exactly the same as part 1. Okay, so are they independent? Well, fxy of x and y, what was it? It's 1 if 0 less than x less than 1, 0 less than y less than 1, and it's 0 otherwise. Alright, so what about f of y times f of x? Well, f of x is 1 when x is between 0 and 1, and 0 otherwise. F of y is 1 for y between 0 and 1, and 0 otherwise. So what is fx of y? Well, you can work it out. 1 times 1. It's exactly this. It's exactly the joint PDF, right? So fx times fy is equal to 1 times 1 if 0 less than x less than 1, 0 less than y less than 1. Obviously 1 times 1 is 1, and it's 0 otherwise. That should be a 1. Okay, so fx of x, fy of y equals the joint everywhere. Exactly the same function. So x and y are independent. This little upside down t means independent. All right. We've got 2 minutes left, so I think I'm not proving. Sorry, I didn't. We've got 2 minutes left, so I think we'll call it a day there, and we'll resume next week.